Hello, Miss Mary, Miss Rana, right?
Yeah.
Okay, so we talk about this lucky number, 78, right? Originally it was 47, but you said 78 is more luckier than 47.
No,
Okay.
we just said that in Chinese, 4 is not lucky. 4 is bad. Basically, Seth.
Okay, yeah, it sounds similar to that. Okay, so we talked about finding the nth lucky number. One thing we observe is that we can map this using binary. We map 0 to 7, 1 to 8. It's mapping to the next number because the first lucky number is 7, is not 0. Okay, so that's why there's a 1 difference. Okay, by looking at this, what other things we can get? For example, like look, if we want to find the 8th lucky number, which is 778, what does it equal? If I remove this A, which lucky number is it? Which lucky number is it? If I remove this A, which lucky number is it?
3.
3, okay. Okay, so yes, okay. Look, 8, this is to 3. And the 7th lucky number, which is 777. So it's 77 plus 7. So which one is it? Is it the same, yeah? Is this mapped to the 3, okay? So basically 7 is 3 plus 7. 8 is the third lucky number plus 8, okay? And how about 9? Look, 9, 7, 8, which is the fourth lucky number plus 7. The 10th, which is the fourth lucky number plus 8. So do you find something here? Do you find something here?
Yeah, that's what I was saying before.
Yeah, okay. So this,
The last one.
yeah, so look, for example, we can double check this. 6, this is 2 plus the second lucky number plus 8. And the fifth lucky number is the second lucky number plus 7. So we have this recursion. So the recursion formula defined Fn, which return a star. So if the base case, and these two are the base case. If n equal 1, return 7. If n equal 2, return 8, right? This is the base 2 cases. The first and second lucky number we know is 7 and 8. Then the half of it, the previous one, okay? The previous one index equals the n minus 1 divided by 2. Right? Look, A. When it's A, we're looking for the number 3. The third lucky number, right? Yeah? So it's A minus 1 is 7. 7 divided by 2, which is 3.5, and which is 3, the integer part. So the answer is, then we have to check if it's odd number, right? So if n and 1 is 1, if it's odd number, then it return fp plus 7. Otherwise, return fp plus 8. So what happens if I don't define these base cases? What will happen? For the recursion, what will happen if we don't have base cases?
We can't solve it.
We can't solve it, yes, because it's going to recursively call itself until, infinity, right? Am I right? For example, like, the n factorial. N factorial equals n times n minus 1 factorial. N minus 1 factorial equals n minus 1 times n minus 2 factorial, right? So if we don't tell the computer f0, the n0 factorial is 1, 1 factorial is 1, then it's going to recursively call infinity. So for recursion, we need to define the base case, which is this part. For example, fa, according to this, is equals to f3 plus a, right? f3, this bit is f3. Okay, so now f3 equals f1, which is this bit plus 7, right? And then we can put a cache, right? Yeah, right? We can put a cache, but for this one, the cache doesn't help much because it's one single call, right? So we want to call the fn, it depends on fn minus 1 divided by 2. The number of calls is log to n, right? Because every time the n is half, right? In order to calculate f10, I need the value of f4. In order to calculate f4, I need the value of f1, right? So every time the n is half, so log n, okay? So this cache is not much useful. The cache is useful if we want to calculate fn and it needs to call to f, another n smaller n, n1, smaller than n2. If they are more than one recursive calls, then possibly we use the cache to save the intermediate result. One typical example is the Fibonacci number. Okay, Fibonacci number. So previously we're using the binary, which is also the log n, and today we're using the recursion. Okay. Okay, what have you learned today?
Basically the same thing as yesterday, last week.
What's the approach we're using today?
We use the recursion.
Yeah. How do we recursively solve this problem? What's the recursion? How do we recursively solve this problem?
Use cache so it doesn't repeat.
So we look in this F9. So this is 7a plus 7, right? F10 is 7a plus 8. So 7a is F4 here. So basically we need to find out the value of F4 and plus 7 plus 8 here. And F4 is equals to F1 plus 8. Okay, F3 is equals F1 plus 7. We're solving a smaller problem. So we use the result for the smaller problem and then we construct the bigger answer for the bigger n. Okay, so in this case we can solve all the fn. By looking at this table, we summarize this pattern. So basically we are implementing this recursion based on this pattern we are seeing. It's similar to the binary. Okay, okay, that's it for today. Bye bye. Bye bye.
Bye.
Bye.